Before we get started, let's just have a quick conversation here. There's a lot of projects going on simultaneously in this room. Honestly, probably way too many. It definitely way too many, but there's just so much cool stuff going on here. The Centurion is just this beautiful piece of equipment, and there's still so much more to repair and restore and learn about that machine, and I think people are really amped up about it. And the PDP-1144 I'm chomping at the bit to get back into because that Fujitsu Eagle drive is just calling my name, and it's a really cool look into history. The PDP-11 was an incredibly important machine in computing history. But there's so much more going on here. I really want to get back into TI-99 stuff, or notably TMS 9900 based stuff. I really want to build a homebrew based around that. The Lytton is waiting in the wings. We've got the Data 620. We've got smaller machines like the NEC PC 8001 and my ADM3A terminal, which has suddenly decided to stop working. So there's a lot more stuff to do, but the reason that I'm standing here in this position is because of these two machines. This is the UE1 vacuum tube computer that is a homebrew computer I'm building from scratch, and this is a Bendix G15, a full-fledged vacuum tube computer from 1956. But it's hard to call both of these computers because currently neither of them work. The UE1, the processor side of it, does work. You can plug the remote control into it and do stuff with it, but that doesn't feel like a computer. A computer needs input and output and a program running through telling it to do stuff and blinking lights flashing around, and that's what we're building on it, but as you can see, it hasn't been built yet. And the Bendix G15 boots up correctly. Everything gets through the boot process 100% perfectly. All the correct data finds its way onto the drum, but when you flip the go switch to tell it to start executing, it just sits there completely inert. And I promised Bob that the G15 would be executing code before the end of 2024. And I genuinely thought that the UE1 would be done by the end of 2023. Here we are, marching into November, and neither of these things work. So, you know what? I'm gonna make an executive decision right now. All other projects in the room are on hold until both of these are doing something exciting. So I hope you like vacuum tube computers because it's tube computer or bust. We are going hard on these until 2025 because I want to see both of these executing code by 2025. So let's get started. So what is it that we're trying to do? Well, we're trying to build a vacuum tube version of this, and this is the minimal ICU system as outlined by Motorola in the MC14500 handbook. And the MC14500 is a 1-bit industrial control unit built by Motorola in the late 70s to replace relay ladder logic in industrial situations. But it is a full-fledged 1-bit microprocessor, and that kind of is what started this whole project. I wanted to see if I could build a vacuum tube version of that microprocessor. And along the way, I was pretty frustrated with the logic unit in it, so I upgraded it to a proper arithmetic logic unit, which necessitated having a carry register. And so we can do proper addition and subtraction now. But it's important to note that both my vacuum tube version of it and the original Motorola version of it are 1-bit CPUs. They have a 1-bit data bus, and that classifies them as a 1-bit CPU, regardless of how big the instruction bus is or the address bus. We've got that built, it's fully functioning. So the next step is to build everything else in this minimal ICU system here. But this diagram here doesn't really work very well for what we're building because there's a couple of large changes that we had to make. We've got our UE1 CPU over here on the left, and this puts out a couple of important signals that ultimately feed into our 1-bit data bus. Now we have a 4-bit instruction coming into the UE1 CPU. This is telling it what to do. And then we have a 4-bit memory address that we're using in kind of interesting ways to either select 8 bits of random access memory, a loopback of the results register back into the data bus, 7 bits of external input, or 8 bits of external output. So we're using that 4-bit memory address plus the write signal coming from the CPU to address more than just 16 locations. So we have a 4-bit instruction and a 4-bit memory address that is just 8 bits or 1 byte, and it just so happens that 8-level paper tape has 8 levels or 8 bits per column here, which means that we can use paper tape to effectively become our ROM, our read-only memory that contains the stored program that is executing on the CPU. Now, in the previous episode, I built up a little block out of aluminum that holds photodiodes. Now, before you jump in the comments and say, photodiodes are not vacuum tube computer period correct, that's not true. The Bendix G15 is from 1956 and it uses photodiodes on it. And I'm actually using almost identical photodiodes that are in it. So we're still remaining within period correctness for the mid-1950s vacuum tube computer that I was using kind of to guide my construction process here. But in the previous episode, we built up that photodiode block and we had the paper tape pulling through it and we could see that it lined up. And I said that I need to build some kind of motorized contraption that pulls that tape through automatically for us. And a ton of people left comments saying, why don't I just hook it up to the system as is and pull the paper tape through by hand? And that is an excellent idea if you have a system that is more capable than the system that we have. Normally on a computer like say a PDP-8, when you read in a program off of paper tape, what happens is it reads in the bytes, copies them from the paper tape over into random access memory, and then when you're done reading the paper tape in, you tell it to jump to that point in random access memory and start executing instructions out of memory. But we don't have RAM. We have 1 byte of random access memory. That is 1 instruction, and we need to have maybe 1,000 instructions or something like that. And so we're going to be executing the instruction directly off of the paper tape. It is read from the paper tape, and that is executing everything else on the CPU. Also, the entire processor is built around the concept of loops. We can't jump, but we can mask input and output based upon results in the result register. So that way we can have a tape running in loops and we can execute different blocks of code on that tape. And that's essentially like jumping back and forth within our program. So we have to build something that has an electric motor that is pulling the tape through our phototape reader and able to essentially run indefinitely on a paper tape loop. And I was talking with the people over on the Discord, and Chris had a really interesting suggestion, and that was to use a slot car motor. These are very small, compact DC motors that were used in slot car racers that were really popular in the 1960s. And that fit the bill perfectly, except for the fact that they spin too fast. But because this is now a hobby that's been going on for like 50, 60 years, there's gear reduction sets out there that you can buy for like $3 on eBay. So I ordered up some of these motors because they looked like they were going to be absolutely perfect. And once I had them in hand, I needed to come up with a way to essentially gear it down and change the direction so that it could be used as a capstan to pull paper tape through. And I was kind of sitting on this, procrastinating. I didn't really know a good way to do it until I was recently up in Pittsburgh visiting my brother. And my brother has this amazing shop in Pittsburgh called Lovett Sundries. If you guys haven't heard of Lovett Sundries, please go check him out. They've just built this absolutely beautiful store and they sell some of the most amazing products, and I am beyond proud of what my brother and his wife have built from essentially nothing. It's absolutely stunning, and it's pretty much my home away from home. So I brought up this idea that I need to build something to hold this slot car motor with a gear reduction and essentially change direction with a capstan and a roller and all of this. And I brought that up with my brother and he said, hey, you know what? I've got FreeCAD installed. Why don't we sit down and have a bit of a lesson about FreeCAD? Because that was something that I really wanted to learn anyways. So we sat down and we started designing on FreeCAD, and based off on some measurements of the motor and measurements of the gear reductions, we came up with a design. You can see a little bit of it right here. And I think this design is gonna work perfectly. But now that I have the design, what next? I gotta essentially take these measurements home and then machine them out? Well, Lovett Sundries has a secret hiding out in the basement, and that is that my brother has built a pretty awesome machine shop down there that is very, very capable. And you can see Jeff here actually finishing up a project on his lathe, and it was coming out absolutely beautifully. Just look at the fit and finish of this piece that he's been building. But now that we've got that squared away, it's time to get started on the UE1 reader project. And we've got some nice printouts of the design to follow, and credit where credit is due, Jeff drew these up in FreeCAD, but my good buddy John from CAD Industries was in town visiting as well, so we wrangled him into giving his seal of approval too. And if you don't know about CAD Industries, check them out. John is a very close friend, and he also happens to be running an extremely capable metal shop up in Massachusetts. He's been turning large pieces of metal into smaller pieces of metal for decades, so having his experience nearby was just fantastic. So here we've got our piece of aluminum stock out, and Jeff is painting on something called dichem. This is a blue fluid that you can paint onto metal, and it adheres well enough for working with, but also it can be easily removed with acetone so you can clean it up later. But the reason that we're painting this piece blue is so we can lay out some lines showing where we want to cut. We will of course be measuring it properly while cutting, but this is an excellent reference for roughing. And speaking of roughing, this piece of aluminum stock is a little too big and unwieldy to mount in the mill, so it's off to the bandsaw to trim it down to a more manageable size. But because the bandsaw is essentially doing it by hand, the edges are nowhere near perfectly flat or straight, which means it's finally time to fire up the mill. Now, this is not a CNC mill, but it does have a DRO, or a digital readout, and a power feed on the X-axis. We're taking reasonable cuts on the first side to get it nice and flat. Then we'll flip it over and flatten off the other side. We're using IPA as a cutting fluid here, and before you go crazy, it's cheap, and as long as you're cutting aluminum, there isn't any danger from using it. Don't use IPA if you're cutting steel though. However, it does tend to remove some of the dichem, which is an unexpected side effect. Once the width is on point, it's time to start getting the length down. The procedure is largely the same. Flatten one side of the block, flip it around, and then bring the other side of the block back until it's the correct length. And now we have a properly sized block. It's time for the first big boy cut. And with John guiding us on proper speeds and feeds and depths, well, just look at that cut. It's cutting beautifully well, and we're taking about 3 times worth of material on one cut than I would have felt comfortable doing. But having John lend his expertise here really let us lean into the mill, and the little Precision Matthews mill here performed beautifully. And speaking of John, we were all chomping at the bit to make aluminum chips, and John stepped up and got some machining time in as well. Watching the master work was both a ton of fun and incredibly educational. We were making all sorts of progress, and John had the speeds and feeds dialed in perfectly. One thing that blew my mind is that the chips that were coming off were being cut so cleanly and cooled so well by the IPA that you could actually catch them in your hand fresh off the mill, and it wouldn't burn you at all. They were just mildly warm, which just reiterates that we had the little mill dialed in perfectly. The cutting went smooth as butter, and the piece came out amazingly well. And here you can see the finished piece with the electric motor and gear set laid down in place, and it turned out amazing. Since I've got the motor in hand, let's tear it down and clean it up. The brushes come off with just a single screw, then the front bushing is held on with 2 screws. With those removed, it slides right off the front, then the armature can be pulled out behind it. But be careful, there are little washers used as shims and they can go flying if you're not careful. I'll pull out a Scotch-Brite pad and clean up both the brush's contact points as well as the shaft itself. Then we'll put some light oil in where the shaft will slot into place and get the armature back into the motor. Then we just slide the top bushing back into place, and it's time to give the little motor some electrons. We can see that it spins and spins well, even at a wide range of voltages. It'll spin at anywhere between about 3 volts to 12 volts, which makes sense. This is how you would adjust the speed of slot cars back in the day, by just changing the voltage that the motor saw. But that little spinning shaft is useless unless there's a gear on it. The gear set I ordered is the right size, but the tiny bevel gear doesn't appear to be a press fit. I read around and it seemed that a popular way of attaching gears like this can be to solder them on. So that's what I opted for here because my little welder can put out some serious heat. Next, I need to get the motor and gear set mounted, which means I gotta drill some holes in our beautiful chunk of aluminum. The motor has 2 threaded mounting holes on the side, so I'll punch a hole in the right location, but the machine screws that I'm using are too short, so I gotta countersink them, and I think this will look better anyways. I just used a big enough drill bit with some tape on it so that I knew how deep to cut, and that worked an absolute treat. With the motor mounted, I need to work on the upper brace for the shaft. I drilled 2 more holes, then pulled out the 6x32 tap and threaded them up. After drilling a hole in the base for the shaft, I can see that it's all starting to take shape. I'll just cinch the upper brace down nice and tight and then promptly remember that I need to solder some wires to the motor, so it's all gotta come apart again. With wires soldered on, I can snake them through a hole in the side that I drilled for them, and this keeps them clean and out of the way. And with the motor mounted again, it's time to install the gear set and shaft again. Let's give this thing some juice, and heck yeah, it spins and spins well. I let it just sit there and run for about 30 minutes, and it got progressively better as oil worked its way onto the shaft and the brushes burned themselves clean. Now I need a backing plate to mount all this stuff too, and I just so happen to have this spare piece of aluminum, but it's unfortunately got about 900,000 holes in it. It does look like there's a nice rectangle here in the middle that's hole free though, so that's what I'm gonna use. And there's a million different ways to cut aluminum, but I'm opting for the skill saw here. It's super easy to use and makes surprisingly clean cuts, but not quite clean enough. I need to actually clean up the edges on the belt sander here, which didn't actually take all that long. The belt sander is a fantastic tool to have in the shop. Then let's mock up the layout here with the tape drive and optical reader. After bolting it down, it's time to figure out the pinch roller. I need to grab some measurements just to be double sure, and then I'm going to draw out the piece that I want to build. This is going to sandwich in between the base piece and the shaft support, and in order to make the slot, I need to drill a large hole first and then slice out the excess. I ended up doing this by hand because it seemed the safest way without ruining the piece, but it means I gotta spend a lot of time with a file cleaning it up. Once it's in place, that's starting to look really good. I also installed an adjustable guide on the backside. This should ensure that the paper tape is properly aligned with the photodiode reader. Finally, I want to make some tensioning posts. I grabbed some long bolts and slapped them in the lathe, then I slowly worked back and forth cutting off the threads. I want to leave the threads near the head of the bolt though, so I can actually bolt the thing to the bottom plate. And then finally, they'll all get a good sand to smooth them out. And here's the finished product, and it looks absolutely stunning, but looks don't mean anything unless it actually functions as well. So does it move tape? Well, let's find out. Look at it pulling tape through. Look at it go. It pulled the tape completely through. There's about 9 million adjustments that need to be made on here. Particularly the tension between the pinch roller and the capstan here needs to be set correctly because I can load up the motor and make it behave really awkwardly. But that's moderately easy to adjust with the lock nut here. I can just loosen it up and move that whole pinch roller back and forth. And also I need to make sure that the alignment of our guide here is perfect with the photodiode block here. I mean, it seems to be pretty good because the tape isn't catching at all. But the biggest problem that we have are these 2 tension posts back here. They're garbage. I need to just throw them away and come up with something else. They're way too skinny, so I need something a lot thicker that can go around them and a lot smoother because otherwise they create too much tension and the tape just slips. It is super loud, but I'm hoping that that'll quieten down as I get the adjustments correct and I get the backlash on the gear set correctly. There's a bunch of different ways that I can adjust this and it's just kind of slapped together at the moment. But even in a slapped together state, it pulled the tape through perfectly. That is, oh, that's so good. That's such a huge relief. So what's next, aside from adjustments and these two tension posts back here? Well, it's still missing some stuff. We don't have a light source up here, so I need to build a bracket that holds 2 light bulbs that's gonna shine directly into there with probably some light guides so that it's very, very bright right on the front here. I also need to make the PCB that's gonna sit on the back here that all of the photodiodes plug into. And then I need to create a plug that goes from that to a harness that ultimately then goes back up to the rest of the machine. Then I gotta figure out how to get this board mounted on the main backing board, figure out if there's any kind of additional vacuum tubes or expansion that we need to put onto that main backing board. We need to build a bucket that sits underneath it to hold the excess tape loop whenever it's looping around. And I need to redo the inverter, buffer, and clock boards that are on that backboard up there already. So I need to pull those down, change out some resistors, and then cut a couple of new PCBs for that. And then, boy, we're getting real close to being able to just plug things in and see what happens and what moves where. So I'm gonna be right back on this next week because it's vacuum tube computer or bust here at Usagi Electric, and we're gonna get that UE1 doing some pretty epic stuff. So I wanna thank you all so much for watching, and I hope to see you in the next episode.